In video 2C, where our next topic actually is going to be the distance formula, but in order to really understand the distance formula, we need to talk about the Pythagorean theorem. So over here on the side, I'd like you to draw yourself a nice right triangle. Remember, a right triangle has a 90-degree angle in it. I want us to go name the three sides. For a right triangle, the longest side, which is always across from the right angle, is called the hypotenuse. Kind of a weird word, isn't it? And the other two sides adjacent, another word we've talked about already, oops, I forgot the E, to the right angle are called the legs. So we call this leg and we call this one a leg. What Pythagoras did, he was a Greek mathematician. Actually, he's kind of a weird guy. I had some students do a math history project, and one of them did a biography kind of Pythagoras. He's just a weird guy. He had his own like religious cult that followed him, and they called themselves the Pythagorean theorem, but not the Pythagorean theorem, sorry, the Pythagoreans, and they had just a bunch of really weird beliefs. But I'm kind of getting off topic here. What Pythagoras discovered is, and it doesn't sound like a big deal, but it really kind of is a big deal when you get into construction and some kinds of engineering and higher levels of math, and there's a lot of stuff involves the Pythagorean theorem. You wouldn't think it would, but it does. And what he discovered is that if, this only works for right triangles, so it has the hypothesis that if a triangle is right, or is a right triangle, then what always happens is that the length of a leg squared plus the length of the other leg squared will always equal the hypotenuse. I'm running out of room in my box on here. There we go, hypotenuse squared. So what we do in math when things get too wordy is we make variables to represent the words. So in the right triangle scenario, the legs are always called A and B, and the hypotenuse is always called C, and that's always across from the right angle. So really we get A squared plus B squared will always equal C squared. Be careful that you don't think you can just throw the numbers in anywhere, because it does matter. We always locate C because that's important. Addition's commutative, so you don't really need to care who's A or who's B because it doesn't matter. What do I mean by addition is commutative? 3 plus 5 and 5 plus 3 both yield 8. So it doesn't matter which leg you call A or which leg you call B, because with the addition, the order doesn't matter. But it does matter that C is always on the right-hand side of the equals. So C is the kicker. I can't just throw this in for A and this in for B. I can't do that. The one across from the right angle is C. So I'm thinking leg squared plus leg squared is hypotenuse squared. One of the legs is 13. The other one is x. I'm going to square them, add them up, and set them equal to 15 squared. Then I go to my calculator, or I know it by heart, and I do 13 squared, or 13 times 13, and I get that changed red for no reason, and I get 169. Plus x squared has to equal 15 times 15, or 15 squared, which is 225. My goal is to attack this for x, so I'm going to use my solving skills to get the 169 off of there. I'm going to either use a calculator if available, or I'll do it by hand, and I don't have a calculator on me right now, so I'm going to take this out by hand, doing a little borrowing here. I'm going to subtract, and I get 15 minus 9 is 6, 11 minus 6 is 5, and I get x squared is 56. To undo a square, its inverse operation is to square root. So these always end in square rooting both sides. How do they always end? Answer, square root both sides. And I get x is equal to I'm going to go write this over here because I don't want to run into the next problem. X is equal to the square root of 56. Now you might be tempted to go get your calculator and round that, but this says simplest radical form, which we've already discussed in a previous lesson, how we get this into simplest. I'm going to move this over a little bit. Sorry, I want to get access to my scroll bar, so you're going to see a little movement. There we go. I want to be able to scroll here. So how do I get this in simplest radical form? Remember what that requires. It's a hunt. It's a hunt for that biggest perfect square that's hiding out in the number 56. 1 is a perfect square, but it's never helpful. So 1's going to be put down, but I'm not going to use it. I'm going to write these in green just so they stand out a little more. So come on. All right, here we go. 4 is a perfect square. 3 times 3 is. Notice I'm not memorizing, I'm creating them. 4 times 4, 5 times 5, 6 times 6, and we need never look beyond half of this number. What I just said seems minor, but it is kind of good to note. You never need to look past half of the number. So any number that goes in there evenly has to be one of these. Well, I know 25 doesn't go in there, so 16 is my first candidate. 16 times 3 is 48. So there's no way 16 is going into 56. It's just not. And 9 doesn't go into 56. But 4 does. So what I'm going to do here is I'm going to break this up into, you might say, how do you know 4 does? Well, I just know. But if you don't, you go to a calculator and you divide them or you do it by hand. I get a 1, 4, 16, and a 4. So I do know that it breaks up into a nice perfect square and another one that I don't know. So when I write this in simplest radical form, my answer is 2 times the square root of 14. So be careful how it says to write your answer. If you're allowed to go to a decimal, go ahead and use a calculator right here and round to what it tells you to. But if not, you have to be prepared to simplify that, which we've already covered in another section. So the next thing is we can also use what's called the converse of the Pythagorean theorem. A converse means to switch the if and the then. So the Pythagorean theorem says if a triangle is a right triangle, then a squared plus b squared equals c squared. Well, its converse says if, I'm going to swap this, a squared plus b squared equals c squared, then oopsie, then the triangle is a right triangle. So for you to test, you might say, well, it looks right. I'm going to go measure it. You don't know. Maybe this right here is 90.00005 degrees. Then it's not a right triangle. It's obtuse. So you got to be careful. You can't go by looks unless they've got the marking in there and you have that little box in there indicating that those are perpendicular and a right angle. This does not have that in there. By the way, though, if it was in there, if this was sitting there, I'd say, yep, it's right. But without it, I have to run a test. I have to see, does leg squared, this is how you know if something's built at a right angle, by the way. If it's not, it's going to be a little kitty wampus, but you can just check if a squared plus b squared equals c squared, whatever you're building is built what they call it building it square. That's why oh, whatever. I don't want to go off on a tangent again. I already went on my Pythagorean tangent. So let's go figure this out. If the leg squared plus the leg squared equals the hypotenuse squared, the hypotenuse is always the longest side across from the right angle. So if this is a right triangle, 16 would be the hypotenuse. So I just got to run a little check here. Does the leg squared, one of the ones adjacent to what might be the right angle, plus the other one, you got to be careful how you write this. Don't put a little 2 like that because that would only square the root 39. We need to square the entire leg, just not part of it. Does that equal the hypotenuse squared? And this is up for question, so I'm going to put a little question mark here. And then I'm going to go see if they match. 10 times 10 is 100. When I square this, I do it times itself. 2 times 2 is 4. Root 39 times root 39 is just 39. You can do that on your calculator if you don't trust me. Does that equal 16 times 16, which is 256? I don't know, I got to go check. I got to go do 4 times 39. You can either do that by hand or on a calculator, but 4 times 39 will end up being 156. So the question is, are these equal? And I can see here right now that yes, they are equal. So what that means is this is for sure a right angle. So the answer is, yeah, you betcha. All right, so why are we discussing the Pythagorean theorem? The reason is because our next topic up for discussion here, I need to access my page turner. Come on, turn the page. There we go. We're going to do the distance formula next. And the distance formula is really the Pythagorean theorem, to be honest with you. But if you're looking for the distance between 2 points on a graph, so I want to know how far is it from red dot to red dot. If it's graphed, I wouldn't use a formula. I'm going to give you one. But if it's graphed, use the Pythagorean theorem because that's so easy and clean. Make a right triangle out of it on your graph. You're looking for the hypotenuse. Count the boxes to figure out how long each leg is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I've got I've got a isosceles right triangle sitting here, and I need to figure out the length of the hypotenuse. So I go a squared, leg squared, plus b squared, the other leg squared, is equal to c squared. And that's the distance I'm looking for because I want to know my end answer is what's the distance between these 2 points? What's the hypotenuse of a right triangle? 5 times 5 is 25, never 10. 5 times 5 is 25, never 10. And that's equal to c squared. 25 plus 25 is 50. And so why did I write a 2? Just trying to see if you're paying attention, that's why. So I've got 50 is equal to c squared. Again, to undo a square, you square root. These always end in taking a square root. The square root of anything squared is itself. They're inverse operations. And I've got the square root of 50. And then it depends how I'm told to get my answer. This one didn't say, so you probably could go to your calculator, take the root and round it. But let's keep this in exact simplified form. Who is my perfect square hiding out? You might say, how's she listing those so fast? 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5. The minute I write this, I'm like, score. I found a really nice big perfect square hiding in the square root of 50. And so I break it apart. I know this is 5, and I say 5 root 2 is this length. But really, you might want to go decimal for that. And if on your calculator you did the square root of 50, you're going to get 7.07-ish. That needs to be rounded, so it's no longer what we'd call an exact answer. But the length of this is 7.07 boxes. So it's just about 7 of these little lengths with a tiny little bit more. But what if you're not given the graph? What if you're given just 2 points sitting there? Could you go get graph paper and plot them and use the Pythagorean theorem? The answer is yes. Usually that's not an option. I mean, I suppose you could always just Google graph paper and then print off a slice, but there's an alternative. There's a formula. So when you're given 2 points, instead of having them plotted on a graph, they're just given to you as coordinates. Like right here, these aren't graphed, they're just 2 points somewhere in space, and I don't want to graph them. Could you still figure out how far apart they are? And the answer is yes. So you have 2 points, and let's say one of them is point C, and go like that, come on, and one of them is point D. If I wanted to know what is the distance from C to D, a lot of times we call that D. Sometimes because this is between C and D, we'll say the length of CD. Remember, we've talked about that, how without any marking over it. Let's go here, line segment, ray, line, length is given by the square root of We subtract the x's in the formula, but really what that's giving you, back up to this picture up here, really when you subtract the x's, look where I'm writing in green, you're getting this length. So it's the square root of x2 minus x1 quantity squared. That's really what I did though. I figured out how many boxes are there. They were 5 apart, and I squared it. And then I added to it how far apart were the y's. But really, if I can't see the graph to figure out how far apart they are, I subtract them. And a squared plus b squared equals c squared. So remember, once I had my 25 plus 25 equaled c squared up above, I just don't want to scroll, I said 50 equaled c squared. So I had to take the root. So that's where this root is coming from. So really the distance formula is an alternative form of the Pythagorean theorem. Let's go apply it. I'm to find the distance between these 2 points. In this scenario, 3 would be considered the first x, 9 would be considered the second x, 8 would be considered the first y, and 10 would be, went red again, that's so weird, would be considered the second y. I'm supposed to write my answer as a simplified radical form. That means no decimals. Your answer should have a root in it. And then I'm also going to round it to 2 decimal places, so to the hundredths place. What does my formula say? My formula says that the distance between those 2 points is found by taking the, I'm changing colors if you're wondering what all that clicking is, square root, so look in purple, of x2, 9, minus, it's like a map, formulas are just maps, just follow the directions, x1, which is a 3, I'm supposed to group them, square them, and add to it the exact same thing with the y's. y2 minus y1 squared. Now I just need to go execute this. Let's go do it. What is 9 minus 3? 6. What is 10 minus 8? 2. 6 times 6 is 36, never 12. 2 times 2 is 4. I add those together. I get the square root of 40. Now let's stop. It said to give my answer in simplified radical form. I'm going to do that along this stretch of the road. And as a decimal, rounded to 2 decimal place. Let's do the decimal first. To do the decimal, you'd go to your calculator and you do the square root of. If you don't know where that is on your particular calculator, just come and ask me. And you'd get 6.324. Because the one next to the second decimal place is a 4, I won't do anything with that 2. Again, if it was like a 7, I'd have to bump that up to a 3. Remember your rounding rules. But that's the answer rounded to 2 decimal places. My answer as a simplified radical would be to find the perfect square hiding in 40. And you might say, I know, 40 is 5 times 8. That's great, but neither one of those is my perfect square. So it doesn't help me to break 1 I don't know into 2 I don't know. So I don't want to do that. I'm looking for a perfect square hiding in 40. 1 times 1, 2 times 2, hey, there's 1. 4 times 10. And I know it's the biggest one too because 10 doesn't have any more perfect squares in it. It's got a 2 and a 5 and those aren't in my list. Remember the next one is 9. 2 and 5 are not perfect squares. So I've got root 4, which I know to be 2, and root 10, which nobody knows because remember it goes on forever and it never repeats. So these are equivalent answers. One's a decimal version and one's a radical or root version. And that's it. Your next assignment is to do worksheet 2.5 and worksheet 2.6. Have a good one.